good afternoon, good morning, good evening, ladies and gentlemen, and thank you again for attending our webinar. We have carried out this study last year aiming to find out which renewable electric technologies have the best potential to achieve EU energy targets in both saving CO2 emissions and reducing the use of the overall energy in residential dwellings. We have also tried to assess how attractive such technologies can be for the end user from operating and lifetime cost point of view. Here is my picture so that you can put the face to the voice. And now I will carry on with methodology assumptions. Following renewable technologies have been taken into consideration: electric heat pumps, micro CHP, photovoltaics. They are all called established technologies across the presentation, as well as we have analyzed fuel cells and intelligent controls that are called emerging technologies further on. They have all been set against the high-efficiency gas condensing boiler, which was adopted as a base technology to be enhanced or replaced by renewable products. Among all the assumptions listed here, the most important point is actually to understand that our calculations have taken into account the total energy consumption of the household, not only energy use related to the product or applied system. Product efficiency has been based on available info from manufacturers, as well as from efficiency test programs and on BSRIA own information. Different heat loads had been assumed for existing and for new dwellings in each country. The average size of the products or system in residential dwellings came from the research BSRIA WMI has carried out during the last 10 years of the European renewable market. Here is, for your information, a brief overview of main factors that represent the background of the analysis. Our study has been looking at longer-term perspective with 2030 development in view. Not all of the analyzed countries have a defined 2030 energy targets. However, having the European Energy Roadmap 2050 in mind and targets adopted in some of the leading European countries, we have assumed that the trend in the next 20 years will be to increase the share of earth in electricity production. The choice of technologies presented today is also in relation to this trend. The analysis carried out for the purpose of this study concluded that among electric technologies that have been taken into consideration, heat pumps, intelligent controls, PV and fuel cells represent the highest potential to achieve reductions of CO2 emissions in residential dwellings. It has also been found that dwellings where an electric heat pump is installed together with a PV system can achieve the best savings in running costs for the end user, providing, however, that feed-in tariffs for photovoltaics are available. Unfortunately, due to the high initial investment, only photovoltaic systems installed in countries with generous feed-in tariffs are currently able to compete with a gas condensing boiler in terms of lifetime cost. Continuous financial support has a strong impact on market development. It could be observed at the rapid development of PV markets in Germany, but also at the way the Swedish heat pump market has developed during the last 15 years, reaching maturity that is hardly comparable to any other European market. Although there are not many differences in technologies for existing and new dwellings, it is worth noticing that while in new dwellings, installation of the PV system along with the heat pump and intelligent controls represent the most efficient solution, in existing dwellings, fuel cell and heat pump represent a very good alternative to the gas condensing boiler. Let's look at the reasoning behind these choices. At the beginning, I would like to go through all the analysis we have carried out for existing dwellings. When we look at annual CO2 emissions for established technologies, these are our findings. They are showing that in all countries but Poland, the combination of heat pump and PV system in a dwelling is providing the best saving of CO2 emission. Poland, that you can see here in orange color, represents a very specific example of a country with one of the highest CO2 emission factors due to the fact that nearly 80% of electricity has until now been generated from coal there. Both emissions from heat pumps and a combined heat pump and PV system are much higher than those coming from an installed gas condensing boiler. In all other countries, heat pumps offer savings of CO2 against the gas condensing boiler that can in some countries be nearly doubled when a PV system is installed along. We have taken the impact of PV system on CO2 savings under scrutiny, however, puzzled by the fact that the difference they make in CO2 savings is not that big in Sweden and France, for example. I will try to point your attention to that. When you look at CO2 emissions, PV and heat pumps, these two arrows points are for Sweden and for France. They are actually very, very, very low. But the same emission level for heat pumps only is very low as well. So we tried to look a little bit forward and try to explain why is this happening. Actually, both countries, France and Sweden, have very extremely low CO2 emission factors, and renewable energy sources as well as nuclear power already account for the vast majority of electricity production there. Does it matter? Yes, it does. To better understand the reasoning, please have a look first at the savings of CO2 emissions that can be achieved by heat pumps stand alone. In Poland, where CO2 emission factor is very high, the replacement of the gas condensing boiler by a heat pump currently results in increased CO2 emissions. Germany and UK have currently relatively low share of rest in electricity generation, hence their CO2 emission factors are on the higher side. Replacement of the gas boiler by a heat pump brings low CO2 savings, particularly in Germany. You will surely notice the big difference towards the UK results. It does only partly come from the fact that the CO2 emission factor is lower in the UK. It is to note that the analysis take into consideration the RHI scheme that requires increased insulation level for dwellings with heat pumps installed. Higher insulation results in lower heat load and better efficiency of the heat pump. It is both translating into higher CO2 savings. In Italy and Spain, the share of rest in electricity production is higher than in the UK or in Germany. Hence, CO2 emission factor is lower. Replacement of the gas boiler by a heat pump brings higher savings into CO2 emission. In France and Sweden, where electricity is mostly generated from renewable sources and nuclear power, heat pumps are very effective in saving CO2 emissions. They can save between 90 and 96% of emissions towards the operation of gas condensing boiler. What happens when we add a PV system along with the operating heat pump? When added to a dwelling in Poland, it provides high CO2 savings as it produces CO2 lean electricity. When added to a German dwelling, it still has a strong impact, adding about 47% of CO2 savings. However, a PV system added to a dwelling in Spain or Italy is much less effective, and in France or Sweden, it only increases the CO2 savings by 1 or 2%. With electricity becoming increasingly greener, heat pumps increase their capacity of providing high savings of CO2 emissions over the gas condensing boiler, and the role of PV decreases. It is significant when we think about the developing trend towards the increased share of renewable energy sources in electricity generation in the future. Measured in percentages, the amount of CO2 emission savings saved by, say, standalone heat pump and a combined heat pump and PV system in Sweden and in France is nearly the same. I will try to move the arrow showing you Sweden. You see electric heat pump and PV and heat pump are meeting actually. The same for France. They are at nearly the same level. The gap increases, however, together with the decreasing share of RAS in electricity generation, and is the biggest in Germany, here, and Poland, here and there. Annual CO2 emissions. We have looked at the CO2 saving potential that emerging renewable technologies like fuel cell can represent in existing dwellings and tried to assess the impact of intelligent controls as well. Fuel cells, with their potentially high electric efficiency, are a very good alternative to gas condensing boiler in most countries, but in France, where the very low CO2 emission factor is very favorable for the use of heat pumps. You will probably notice that we have not taken the analysis of fuel cells in Sweden into consideration. This is related to the fact that gas price in Sweden is so extremely high that this is absolutely unlikely that any gas-driven technology will achieve any market penetration, significant market penetration in the future there. As they reduce the use of energy in the household, intelligent controls are most effective in countries with higher CO2 emission factors. So far, from a carbon savings point of view, following technologies can be recommended. Heat pumps, as they are effective in reducing CO2 emissions as a replacement of gas condensing boiler today. Their positive impact on CO2 emission savings will only keep increasing following the carbonization of the grid. Heat pumps can reduce energy demand thanks to their increasing efficiency. They are also having a very bright future with the introduction of the smart grid, as intelligent products are about to enter the market shortly. Intelligent controls will help enhance savings achieved by heat pumps. They will also add to the reduction of overall energy demand. Fuel cells are ideal replacement of gas condensing boilers in countries with higher CO2 emission factor. They are also a good alternative if heat pump cannot, for whatever reason, be installed. More flexible electricity generator as PV system, it can also be part of the smart grid in the future. After we have established which technologies offer the best potential for saving of CO2 emissions, we have looked how attractive they are actually for the end user. Two factors having the biggest impact on operating costs are financial support and energy prices. Gas, as I mentioned before, is extremely expensive in Sweden. So even though electricity is also expensive, heat pumps offer substantial savings over the use of gas condensing boiler in this country. It is also to note that in Sweden, ground source heat pumps are prompted and promoted, and their relatively high efficiency helps maximize the benefits for the end user. Electricity is also expensive in Germany and in Italy. While, however, there is no feed-in tariffs for heat pumps in Germany and operating costs for this product in the country are high, Italian customers can now benefit from this type of support, and it has a big impact on operating costs that in Italy are actually lower when compared to the gas condensing boiler. The benefit of feed-in tariffs for heat pumps can also be observed in the UK, where feed-in tariffs for renewable energy products, including heat pumps, are already approved. Feed-in tariffs play a decisive role for making PV systems attractive. In Germany, UK or France, where they are high, feed-in tariffs significantly help lowering the operating energy cost for dwellings when they are installed. The impact of feed-in tariffs can also be observed on micro-CHP. In Germany, thanks to the feed-in tariffs, this technology can compete in terms of operating costs with a gas condensing boiler or an electric heat pump alone. However, due to the much lower level of tariffs for micro-CHP, it cannot be competitive with a PV system. Similar situation can be observed in the UK and in France. Houses equipped with PV systems are benefiting from the highest savings in operating costs, thanks mostly to the feed-in tariff program. The impact of feed-in tariffs can be assessed comparing the results in Spain, where no feed-in tariffs are actually available, where you can look at the savings that can be achieved in the UK, Germany or France, and look at the same level of savings in Spain, you will see what impact generous feed-in tariffs make in reality. High electricity prices are keeping operating costs high for heat pumps as well. Support by feed-in tariff seems also to be effective for this technology, as the example of the UK and Italy are showing. Heat pumps are the red line, and you can see that the savings achieved by a heat pump with feed-in tariffs available for 7 years are nearing 40%, while in Germany, when there are no feed-in tariffs for heat pumps, the heat pump is actually more expensive to run than a gas condensing boiler. When emerging technologies are added to the analysis of the operating cost, they show very promising results in existing dwellings. Thanks to their relatively high electric efficiency, fuel cells can provide operating costs that is well below the level of a cost for a gas condensing boiler, providing, however, that feed-in tariffs, at least at the level as for micro-CHP units, are available. To make sure you can see, the line showing operating costs for solid oxide fuel cells is the green one here. It's well below any other lines here on this chart. The amount of feed-in tariffs paid matters, as we can see in differences between the operating cost for fuel cells in Germany, UK or France. Germany provides most generous tariffs, while feed-in tariffs for micro-CHP in France are low. UK offer better feed-in tariffs than France, but less attractive than Germany. The particularly good performance of fuel cells in Germany relates also to the very high electricity prices and the amount of electricity that can be used for own usage in the dwelling. Intelligent controls reduce energy usage, hence operating costs decrease in dwellings when they are installed. Their use is important in countries with high electricity prices. In Germany, operating cost of a dwelling with heat pump and intelligent controls installed is similar to the dwelling equipped with only gas condensing boiler. Main findings to keep in mind for operating costs in existing dwellings are that feed-in tariffs are playing an important role in lowering dwellings' energy operation cost. Due to the fact that PV usually benefit from particularly high feed-in tariffs, they prove to be the most effective. Heat pumps alone, when supported by feed-in tariffs, like it is the case in UK and Italy, can also bring good savings in operating costs. While end users usually are aware of the existence of heat pumps, they are often unaware of the potential controls, and intelligent controls in particular have to save them money. They need information campaign to make customers aware of their existence. Residential fuel cells are mostly at the prototype stage at the moment. They seem to be a promising technology for existing dwellings, but their efficiency still needs to be proven in real-life operating conditions. Lifetime cost calculations are under high influence of initial investment needed for each technology. As most of the renewable technologies are still very expensive, the end-user price is reducing efficiency advantages that renewables can bring. Even with purchase incentives that are available in Germany, Poland and France for heat pumps, lifetime cost is higher for heat pumps than for gas condensing boiler. High and long-lasting feed-in tariffs, like for heat pumps in the UK, is very helpful. Just to help you recognize what's happening here on this chart, UK is here, that's the color of the UK, and you can see that heat pumps are actually having slightly better results in the lifetime cost than in all other countries when there is no feed-in tariffs for heat pumps available, with extreme situation in Germany, where lifetime costs for heat pump alone are absolutely soaring. Fuel cell is currently bearing extremely high investment cost and showing competitive level of lifetime cost only with high electricity price and decent feed-in tariff, which is the case in Germany. Intelligent controls can reduce the use of overall energy in a dwelling, and their impact on lowering lifetime cost becomes more significant in countries with high electricity prices, which are Germany, Italy and Spain. Let's have a look at what happens in new dwellings. It is important to remember that new dwellings have a significantly lower heat load. This fact is favorable for the installation of heat pumps, as their efficiency is contributing to lower CO2 emissions. Although in Poland, orange line again, where electricity is very CO2 heavy, heat pumps still cannot provide CO2 savings over gas condensing boiler, they offer savings in CO2 emissions over the gas condensing boiler in all other analyzed countries. As heat load is lower in new dwellings, the overall use of electricity contributes strongly to the level of CO2 emissions. Hence, the strong impact of a PV system in new dwellings. Combination with PV system is enhancing the CO2 savings for new dwellings, resulting in some countries in achieving CO2 neutral houses. You will see in Germany, the savings are actually going into negative numbers, which means that the house is producing more energy than it is using. This chart showing CO2 savings in percentages is summarizing the conclusions. Heat pumps provide savings of CO2 emissions over the gas condensing boiler in new dwellings in all countries, but are particularly effective in countries that generate green electricity, France and Sweden. PV installations are the most effective in reducing CO2 emissions in countries with high CO2 conversion factor. With growing share of renewable energy sources in electricity production, the impact that PV installations have on CO2 savings decreases. Intelligent controls enhance savings of CO2 emissions achieved by heat pumps in new dwellings in all the countries, and fuel cells are very effective in countries where electricity is CO2 heavy. As heat load is lower in new dwellings, fuel cells are producing less electricity than it is the case in existing dwellings. Therefore, their impact in countries with higher share of rest in electricity production is lower in new dwellings. Following technologies are identified as technologies that can achieve the best carbon savings in the long-term perspective. Heat pumps, because they are effective in reducing CO2 emissions when installed in a new dwelling instead of a gas boiler. Their positive impact will keep increasing following the decarbonization process of the grid. Heat pumps help reduce energy demand thanks to their efficiency. They are also becoming intelligent and can play an important role in balancing demand in the smart grid system, acting as energy storage. Intelligent controls enhance energy savings achieved by heat pumps and add to the reduction of overall energy demand. Photovoltaics reduce CO2 emissions significantly in countries where electricity is CO2 heavy. They are the only way of own electricity generation in dwellings with no gas connection, and when combined with energy storage solutions, they can be part of the smart grid of the future. In most analyzed countries, there are no incentives or feed-in tariffs for heat pumps installed in new dwellings. What is interesting, however, is the fact that because of the low heat load and better efficiency that heat pumps can achieve in new, well-insulated dwellings, their operating cost is in most cases lower than running cost of a gas condensing boiler. On the other side, feed-in tariffs are available for micro-CHP and PV installations in new dwellings, making these technologies more attractive for the end user in most of the countries. In countries that offer generous feed-in tariffs for PV, a combination of heat pump and a PV system brings very high savings in operating cost against gas condensing boiler. Feed-in tariffs are available for micro-CHP in UK, Germany and France, and they result in cost savings that are above those achieved by a heat pump. As heat load is lower, energy savings that can be achieved by intelligent controls in new dwellings are having higher impact on reducing the operating cost than in existing dwellings. As per fuel cells, however, although they will not contribute as strongly towards reducing operating costs in new dwellings as in existing ones, they offer lower operating costs than a gas condensing boiler, even in those countries where feed-in tariffs are not applied, which is the case for Italy, Spain and Poland. To summarize the findings on operating cost, we conclude that heat pump provide competitive operation cost against gas condensing boiler in new dwellings, even when they are not financially supported. Micro-CHP and PV offer high savings against gas condensing boiler, but they mainly result from available feed-in tariffs. Intelligent controls have relatively high impact on operating cost in new dwellings. It is important to make customers aware of their saving potential. PV can reduce operating costs very significantly, providing feed-in tariffs are available. Market deployment of storage battery is, however, needed to increase the PV future potential. Although attractive in terms of operating cost in new dwellings, heat pumps lose this advantage when lifetime cost is taken in consideration. It is due to the fact that high initial investment is needed to install a heat pump, and in new dwellings it is not offset by any financial support, would it be purchase incentive or feed-in tariffs. The fact that heat pumps can achieve better efficiency in new dwellings cannot offset high initial cost, and the fact that air-to-water heat pumps have a relatively short lifetime and need to be replaced in the analyzed period of 20 years is also playing an important role. Micro-CHP is in better position as its lifetime is estimated at 20 years. Hence, units do not need to be replaced in the analyzed period. In addition, micro-CHP benefits from feed-in tariffs in some countries, in new as well as in existing dwellings. Intelligent controls hardly impact the lifetime cost in each country, although in most cases they add slightly to their reduction. Fuel cells are currently bearing a very high investment cost, and its electric efficiency is not able to overcome this burden in new dwellings. As a result, its lifetime cost is by far not competitive with gas condensing boiler in the new dwelling. To wrap up all the previous slides, let me remind you overall conclusions of the study. Heat pumps, intelligent controls, photovoltaic systems, and fuel cells offer high CO2 savings in new and existing dwellings on the long term. Their market adoption is highly dependent on feed-in tariffs, on energy prices, on heat loads in dwellings, and on product efficiency. We have provided this analysis based on the level of incentives, feed-in tariffs, energy prices, product efficiency and heat load that do not change over the next 20 years. It would certainly be interesting to know what impact changes of main assumptions like feed-in tariffs or energy prices would have on the future market penetration of these systems. Should you be interested to become actively involved in the project, please let us know. With this, I would like to thank you very much for your attention, and I will await your questions. Thank you.
Okay, thank you, Christina, for your very clear presentation. I know that it's not very easy to squeeze all the findings in your very extensive report into a 45 minutes webcast, but you did very well, so thank you.
Thank you.
We received a few questions, and if all goes well, then I can put them on the screen. Just bear with me. And I'll read them out loud so that you can formulate your answer. So the first question is from Fiona Brocklehurst. She asks you what discount rate was used in the lifetime cost calculations.
This is actually the lifetime cost calculations. This is a tool that BSRIA has developed, and to be honest, I cannot answer these questions very clearly because it is a pretty complicated and complex mathematical analysis. I believe that it has been taken in consideration for the 20 years period, but I'm sorry, I cannot tell you from my head how much it was. If you could wait a day, I will find out from my colleagues and get back to you with this. If it's all right?
Thank you. Yes, I think we can indeed put you two into contact, and then you can answer this question later on by
Yes,
written.
I'm sorry. I just need to clarify that BSRIA is a big organization. We have a very big and extensive technical department, which is providing tools for analysis for WMI, which I am part of. So I do not always know all the details behind the tools that we are using to do the analysis, but I will find out and get back to you.
Okay, thank you. Another question from Charles Youssef. Am I to understand that this exercise is only showing the least painful way on how to get to net zero energy, but it is not necessarily economically viable?
Well, what it is actually showing, I think, is that, in fact, we have set up targets for CO2 emission reductions and energy use reduction, but we still do not have a very clear policy to deploy products that might be the most effective in reducing or in achieving these targets. I mean, you can see that the way financial support for products is applied in many countries is not very consistent, and sometimes it's not certainly helping the deployment of the most efficient technologies. Actually, what we think is that studies like this one will help clarifying the situation and put a little bit of fairness in the way products and technologies are supported.
Okay, excellent. Thank you. Third question is from Charles again. It is clear that PV combined with a heat pump is attractive for Sweden, but the area required for PV will be much larger than other countries given the low solar irradiation. How does this affect costings?
Sweden has only recently started to look at the development of PV systems in the country, and to be honest, it is only viable in the south part of Sweden because of climate, of course. If I remember correctly, there is a possibility to receive also incentives for installation of PV systems, not only feed-in tariffs, but certainly Sweden is one of the examples where the way heat pumps have been deployed in order to reduce both costs for the consumers, but also CO2 emissions and energy overall demand is pretty exemplary, because it has been done consistently, continually for 15 years at least, and it has achieved what it was supposed to do. It's also, as I have mentioned during the presentation, to note that Sweden has always been promoting ground source heat pumps because of their increased efficiency and longer lifetime. You might remember that the fact that air-to-water heat pumps as well as gas condensing boiler have only lifetime of between 10 to 15 years. In the longer term, the replacement cost has quite a strong impact on the overall lifetime cost of the products. Ground source heat pumps have much longer lifetime. They can achieve 20 years, which is also making them quite a viable investment from the long-term perspective.
Okay, thank you. I think that Charles wants to answer on that, so I'll forward his comment. Our research shows that the use of heat pump at part load conditions and when reheating from, say, 55 to 60 degrees will have very low COP. Has this been considered when evaluating the viability of heat pumps? In other words, are we to make a word of caution to EU member states on this issue?
Yes, absolutely. Heat pumps that produce sanitary hot water above 55-60% lose their efficiency, and it has been taken into consideration in this study. Certainly when we have been applying ground analysis for ground source heat pumps that are prevalently used in Sweden but also in Poland, these are heating only heat pumps, which also makes a difference in all the analysis. I mean, it was very difficult in this study to unify all the assumptions, because every country has some particularities. And for example, we had to take ground source heat pumps in consideration in Sweden, while for example in Germany or in France, air source heat pumps have been taken for the analysis. But yes, provision of sanitary hot water, so water of the temperature above 60 degrees Celsius, have been taken in consideration.
Okay, great. Thank you. No more questions from participants, Christina, but I have a question that I want to know. You were mentioning the impact of intelligent controls on lifetime cost and operating cost and CO2 emissions. How, just in a few words, how would intelligent controls influence these parameters?
Intelligent controls are able to control really the use of energy in your house. I mean, we have been looking here mainly at controls that are controlling temperature in the house. So for heat pumps, for example, it would be intelligent controls for underfloor heating, or intelligent controls there can take zoning in consideration, so the variation in temperatures in each room of the house. It is to say that by ability of impacting at every moment the way your house is heating, you can save quite a lot of energy. Some manufacturers assess the savings that can be made between 6 to 10% of the overall heat load of the house. So this is how, I mean, it is also a very long story for development, because we are all going towards the future of operating our heating systems from our mobile phones, like we do with many other things. It's, you know, you can take in consideration, for example, the fact that today I will be staying at work for longer, so I don't need my heating system to kick in at 6 o'clock. It can only kick in at 7:30 because I won't be home before 8. Or you can just say, today I'm staying downstairs in the my friends until midnight, so I don't need my upstairs to be heated extensively before this time. So although it sounds a little bit, you know, flimsy, in fact, if it is done consistently and on the longer term, it can save quite a lot of energy.
Okay, thank you. No more questions at this stage. Maybe I can repeat your question at the end of your presentation, asking people who are interested in considering how we could further refine this study for instance, on the feed-in tariffs and energy prices evolution, where we now considered in the study a status quo for the next 20 years. Please let us know, because we're certainly going further with this study. Okay, if no more questions, then I guess we can hereby adjourn. I thank you all for participating to this webinar. Special thanks again to Christina. Christina, thank you.
Thank you very much as well. Please let me also know that I realize that it is often quite difficult to take in consideration all the information so quickly that have been presented. Should you come up with some more questions slightly later, please don't hesitate to send them to Didert or to myself. We will certainly try to do the best to answer them.
Okay,
and thank
great.
you very much for your attention again.
Okay, thank you, Christina. I wish you all the best and a nice continuation of your day, and hope to welcome you on our next webinar. Bye.
Thank you. Bye.